Welcome back to Applied AI Engineer. By now Atlas can retrieve from a real vector database, but a retriever that simply returns the 5 nearest chunks is naive RAG, and naive RAG fails in predictable, fixable ways. Today we fix them. We'll add a cross-encoder re-ranker for precision, rewrite weak queries with HyDE, force every answer to cite its sources, and teach Atlas to admit when it doesn't know. And we won't hand-wave it, we'll measure retrieval quality for real with recall@k. Everything runs locally, no API key required. Last episode we swapped the toy store for a real vector database, metadata filtering, hybrid search, stable chunk IDs we can cite. Atlas can now fetch the top k nearest chunks for any question. But here's the uncomfortable truth. Nearest in embedding space is not the same as most relevant. The top of the list is often noisy, the right chunk sometimes ranks third instead of first, and when retrieval fails entirely, a naive system happily hallucinates a confident, wrong answer. Each is a named failure mode with a known fix. Here's the plan, one fix per failure. When the ranking is noisy, we re-rank the candidates with a cross-encoder. When the query is too vague to embed well, we rewrite it with HyDE before we search. When an answer can't be verified, we force it to cite the chunk IDs it used. And when retrieval simply misses, we install a refusal gate so Atlas says it doesn't know rather than inventing something. 4 techniques, and at the end, the metric that proves they work. Let's start with the highest leverage fix, re-ranking. Our vector search is fast because it compares pre-computed embeddings, but that speed comes at the cost of precision. A second, slower model can read the query and each chunk together and resort them far more accurately. Let's understand why, then run it. 2 kinds of models, 2 jobs. Our retriever is a biencoder. It embeds query and chunk separately, then compares with cosine. That separation lets you pre-index millions of chunks, but because they never meet during scoring, the ranking near the top is rough. A cross-encoder instead reads the query and one chunk together, in a single pass, and outputs one relevance score. Far more accurate but too slow over a whole corpus. So the pattern writes itself, fetch a generous candidate set cheaply, then re-rank just those few expensively. Here's stage 1, the retriever we already know from earlier episodes, distilled to its essence. We load a small local sentence transformer, embed the whole corpus once at startup, and normalize the vectors so a simple dot product gives us cosine similarity. For any query we embed it, score it against every chunk, and return the top k as chunk ID, text, and score. This is fast and it scales, but it's only the recall stage. Watch what happens when we hold its output up to a sharper judge. Stage 2 is the re-ranker. We load a cross-encoder trained on the MS-Marco relevance task, then for each candidate form a query-chain pair and ask the model to score it. Crucially, Predict sees both texts at once, so it judges actual relevance, not just vector proximity. We resort by that score and keep the best few. The helper at the bottom is the whole pipeline in one line, fetch 8 with the biencoder, re-rank, return the top 3. Recall, then precision. A real run, and exactly the behavior we wanted. Before re-ranking, the biencoder puts the password reset chunk, auth2, at position 2. It looked close because after and charge have some lexical pull, but it's irrelevant to a refund. The cross-encoder reads each chunk against the real question and demotes it to 4th. Notice the scores, the relevant chunk, billing 2, sits at -3.3 while everything else collapses past -10. That huge gap is the cross-encoder telling us, with confidence, which single chunk actually answers the question. Here's the shape in one picture. The query goes into the fast byencoder, which scans the entire corpus and hands back a generous top 8 recall, but with a noisy tail, like that misplaced octo. Those 8 pass to the cross-encoder, which rereads each against the query and rescores it, demoting the imposter and surfacing the relevant chunk with a decisive margin. We keep the top 3 and forward only those to the generator. Cheap recall over everything, expensive precision over a handful, the backbone of production retrieval. A few practical notes. In production you fetch wider than 8, 20 to 50 candidates, then re-rank and keep just 3 to 5, because context is precious and expensive. If you'd rather not host the model, the same idea is one API call away. Cohere and Voyage both sell hosted re-rankers with this exact interface. The cost is one extra pass over a few dozen short chunks, milliseconds, not seconds. And the payoff is largest at small k. Re-ranking sharpens an existing candidate set, but it can't rescue you if the right chunk never got retrieved in the first place. That happens most with short, vague, or oddly phrased questions. The fix works on the query side, and it has a wonderfully counterintuitive trick at its heart. Here's the core insight. A question and its answer are written in different styles, so they often sit in different regions of embedding space. A casual query like "Is my stuff kept in Europe?" shares almost no words with a formal data residency document. HyDE hypothetical document embeddings flips this on its head. Instead of embedding the question, we ask the model to hallucinate a plausible answer first, then embed that. The fake answer needn't be correct, it just needs to look like the documents we're searching. The implementation is small. We shell out to the authenticated Claude CLI. That's how we get a genuine model reply in this environment without an API key, and ask it for a short, plausible answer paragraph in the style of a help center doc. Then HyDE retrieve embeds that hypothetical document instead of the raw question and runs the same retriever as before. One LLM call buys us a query that's shaped like the answers we're hunting for. Let's see the difference it makes. A real run again. The vague query already finds the right chunk, data 1, but only at cosine 0.38, dangerously close to its neighbor. Then Claude drafts a hypothetical answer mentioning Frankfurt, and data centers notice it even invents Dublin, which is fine, it's never shown to the user. We embed that draft, and the same chunk now scores 0.55. A markedly more confident match, with a wider margin over the noise, exactly what protects you when the corpus gets large and crowded. The flow visualized. A vague query enters. Instead of embedding it directly, we route it through the language model, which drafts a hypothetical answer that may not be factually correct. We embed that draft, and because it reads like the documents in our store, its vector lands near the genuine chunk. We retrieve with it and pull back the real answer, data 1, with a stronger score. HyDE trades one extra LLM call for better recall on exactly the queries that hurt most, the short, the vague, the colloquial. HyDE is one member of a broader family called query rewriting, and you choose by symptom. If recall is just slightly thin, query expansion, adding synonyms and related terms, widens the net cheaply. If users ask compound questions, decomposition splits one into several subqueries and retrieves for each. The honest caveat: every rewrite is another LLM call, adding latency and cost, so you apply it where recall genuinely fails, not by default. Measure first, which is exactly what we'll do shortly. We can now retrieve the right chunks reliably. But retrieval is only half of trust. The other half is what the model does with those chunks. A production assistant must show its work and must know its limits. Let's build both into Atlas. Grounding means every sentence the model produces can be traced to a source. The mechanism is simple. We number the retrieved chunks and instruct the model to cite the IDs it used, in brackets, after each sentence. An opaque answer becomes auditable. A user can verify each claim, and in episode 13 our evils will use those same citations to score faithfulness with ragas. The rule cuts both ways. If no chunk supports a claim, the model must refuse rather than fill the gap from memory. Here's how we assemble the prompt. We lay the numbered documents out first. Each line is its chunk ID in brackets followed by the text, then the question, then the rules. Context up front, instructions last, keeps the model from getting confused about what it's been given. The rules do three jobs: answer only from these documents, cite the IDs after each sentence, and if the answer isn't here, give one exact refusal sentence. Those bracketed IDs are literally the citations the model will echo back. The full answer function has two independent layers of humility. First, a hard gate. We re-rank and look at the very top crossencoder score. If even the best chunk scores below -8, our threshold between clearly relevant and off-topic, we refuse immediately and never call the language model. That saves cost and removes any chance of hallucination on a known miss. Only if a chunk clears the gate do we build the cited prompt and generate. The prompt's own refusal instruction is the second, softer safety net behind it. Here's a real grounded answer. Every sentence carries its source, billing to, so anyone reading can trace each claim back to the document it came from. No vague summarizing, no invented refund window. The 14-day ticket rule and the 5 to 10-day timeline both come verbatim from the retrieved chunk. This is the difference between an answer you hope is right and one you can prove is right. For a support assistant, that auditability isn't a nicety, it's the whole product. And here's the other half of trust. We ask Atlas something the corpus doesn't cover, the capital of France. The re-ranker's best score is -11, far below our gate, so the function refuses before ever calling the model. Yes, the model knows the answer is Paris, but an assistant that answers from outside its documents will also confidently invent your refund policy. Refusing on a genuine retrieval miss is a feature, not a bug. A system that knows the limits of its own knowledge is one you can actually deploy. We've made 4 changes and claimed each one helps. But claims aren't engineering, measurement is. The single most important retrieval metric is recall@k, and the beautiful thing is we can compute it for real on a small labeled set, right now, with no model judgment involved. Recall@k asks one blunt question: for each query, did the correct chunk land anywhere in the top k? If recall@5 is 0.6, then 40% of the time the answer was never even handed to the generator, and no prompt engineering can rescue an answer that isn't in the context. That makes recall the ceiling on your whole RAG system's quality. Best of all, it's deterministic and cheap. Label a handful of questions with their correct chunk, then count the hits. No LLM judge, no fuzziness. Here's the harness. Gold is our answer key: 8 questions, each paired with the one chunk that truly answers it, labeled by a human. Recall@k takes any ranking function, runs each question through it, and checks whether the gold chunk appears in the top K. The fraction that hit is the recall. Because we pass the ranking function in as an argument, we can score the bare bindecoder and the bindecoder plus reranker with the same code, a clean A to B test of our most important fix. The verdict, computed for real on our 8 labeled questions. The bindecoder alone gets recall at 1 of 0.88, one question in 8 has the wrong chunk at position 1. Add the reranker and recall at 1 jumps to a perfect 1.0. The correct chunk is now always first. But recall at 3 and 5 are both already saturated, even without re-ranking. That's the honest lesson. On this small clean corpus, re-ranking's whole contribution is at the very top, precisely where a citing assistant needs it most. The same result as a curve. Along the bottom is K, up the side is recall. The bindecoder line starts at 0.88 and climbs to 1 by K equals 3. The re-ranked line is pinned at the top from the first point. The gap lives entirely at small k, the whole argument for re-ranking in one image. You retrieve wide for recall, then re-rank so the best chunk is genuinely first, because a grounded answer can only be as good as the chunk at the top of its context. One caveat to close the loop. Recall at K measures retrieval only, it tells you the right chunk was available, not that the model used it well. The next layer measures the generation itself, faithfulness, meaning the answer stayed true to the chunks, and answer relevancy. Those need a model to judge a model, the LLM's judge pattern, which we'll build with ragas in episode 13. The habit to take away now is universal. Label a small evaluation set early and watch the number move on every change you make. Step back and look at what Atlas became today. It retrieves a wide candidate set with the fast bindecoder, re-ranks with a precise cross-encoder, and keeps the best 3. It rewrites weak queries with HyDE so the right chunk surfaces. It grounds every answer in cited chunk IDs and refuses when retrieval falls below the gate. And we proved the retriever with recall at K rather than trusting intuition. That is a real, trustworthy, advanced RAG system, the last RAG you'll build before we change the game. Let's recap. Re-ranking buys precision at the top of the list. HyDE buys recall on the queries that need it. Citations buy trust, and a refusal gate beats a confident hallucination every time. And you now measure retrieval with recall at K instead of guessing. Here's the bigger shift, though everything so far has been a fixed pipeline, retrieve, then generate, the same path every time. Next episode opens Module C and breaks that mold. In From Chains to Agents we give the model a loop and a set of tools, so it can decide what to do, act, observe the result, and try again. That's where Atlas stops following a script and starts to think. See you there.